Alright, so what I'm going to do is a general introduction to equilibrium, chapter 14, with some stuff that we need to know. First of all, the definition of equilibrium states that the forward and reverse reactions of a chemical reaction occur at equal rates and the concentrations remain the same. In fact, that's one of the ways you can spot equilibrium graphically. Kc value is a ratio then of products concentrations over reactant concentrations. Kc happens to be, or equilibrium happens to be, temperature dependent. A couple rules we're going to focus on is, first, there are no units for K, it's unitless. Products over reactants. Exponents reflect stoichiometric coefficients. So those are the three things that we're going to deal with today, is that we're going to focus on the exponents, and they actually become stoichiometric coefficients, or the stoichiometric coefficients become the exponents when we write out an equation. So the first thing that we're going to do is we are going to look at what equilibrium is. Equilibrium is the rate that rates are equal. So for example, if there are 200 people inside Walmart, let's say this is a Walmart, and every minute 10 people leave, at the same time 10 people go in. After 20 minutes, there would still be 200 people in Walmart. After 40 minutes, there would still be 200 people in Walmart. So what that is it's a representation of a chemical reaction. It reaches where there's no further change in the concentrations, the system is at equilibrium. So the amount of product being created and the amount of reactant going backwards, the amount of reactant being created is equal. So there's no net change in concentration. That's the definition of equilibrium. Okay? So keep that in mind. Now, we do use arrows to represent equilibrium. A two-headed arrow like that, going both ways, represents equilibrium. Old school, before we got to equilibrium, you'd use a single arrow. You could actually change the sizes of the arrows based on if one side is favored or whatnot, but we don't use that. This is the arrow you really need to be able to use, is the double-sided arrow right there. That's the one we care about. Now, next thing. Well, homogeneous equilibrium is the first one we start with. What does that mean? It means it's only in a single phase. If you look right there, gas, gas, and gas. So all these species on the product and reactant side are all the same state. So in this case, it's all gas. Here we have aqueous, aqueous, and aqueous. That's what homogeneous means as far as equilibria. Chemical equilibria, how do we spot it? Remember I told you the Walmart example, 200 people inside, 10 go in, 10 go out. If you look right here, this represents an equilibrium region on a graph because you notice there is no change in the concentration of any of the species A, B, or C. Concentrations here on the side. The kinetic region, when the reaction occurs, you see the concentrations changing back and forth. Equilibrium, the concentrations stay the same or they stay flat. Now, one of the things you have to be able to do is write an equilibrium expression. It's the same thing you had to do last year in honors chemistry. Products go on top, reactants go on bottom. The stoichiometric coefficients become exponents with equilibrium. And it's called the law of mass action. Those values are going to be equal to what's Kc, which is a constant value that we use for equilibrium. The reason we use brackets are used to reflect molarity, concentration as far as molarity goes. So in order to write out an equilibrium expression, you basically put the products on top in brackets, put the reactants on bottom in brackets, and whatever the stoichiometric coefficient is becomes the coefficient. Here's the exact same thing. If you notice, it says concentration on the products on the top, concentration of the reactants on the bottom. If we know what K is, we can solve for some of the missing values, or one of the other mathematical problems is if they gave us concentration for C, D, A, and B, you could do a simple calculation and solve for K. In fact, that's one of the ones you have to do on your homework tonight. All right, what does K mean? K is a number. It basically tells us where we are as far as our reaction. If you look, for example, here, if I plugged in or calculate the Kc for this reaction right here, it comes out to 3.5 times 10 to the 8th. Because I know it's products over reactants in a fraction, so Kc is equal to products over reactants in a fraction. Basically, if this number is larger than 1, it means that products have to be greater than reactants, if it's greater than 1. If Kc is less than 1, that means the reactants on the bottom have to be larger than the products on the top. So mathematically, it tells you just by looking at the number, it tells you the ratio of products to reactants. Some reactions we say are product favored, some reactions we say are reactant favored. What does that look like? Well, take the example right here. If you have a small k, when I say small k, I mean it's less than 1. What that means is you have a lot of reactants. So if you look here, look at in this reaction vessel, all the blue reactants. And you have very little products. You got one little red product right there. That would give me a small k. It's going to be below 1. If I look here, a large k is represented by a lot of products. So remember that fraction, products over reactants, right? Equals Kc. That's just the general idea. Look at all the green products I have and very few reactants. Large amount of products, very small amount of reactants. I'm going to get a Kc value greater than 1. Intermediate K, if it's about equal, it's going to be pretty close to 1. That would be an intermediate K. Now, look here. Well, they give us some Kc values for some reactions. I look at the Kc value, 1.212 times 10 to the 9th. That is greater than 1. Therefore, I'm going to say that is a product favored reaction. So it's product favored. I look at this one. My Kc value, 2.0 times 10 to the negative 17th. I would say that this is a reactant favored reaction because the value for Kc is less than 1. Look right here. Kc value of 2.7 times 10 to the negative 18th. This is reactant favored. That's how I get that value. This value is going to be product favored because it is greater than 1. Look at the exponent to the power of 10 is really the way you do it. If you look right here, that's to the 13th, positive, so therefore it's got to favor the products. Heterogeneous equilibrium. We talked about homogeneous equilibrium. That's all if it's in the same state. Hetero means different, so basically you have different states of matter combined together. The key thing to remember with heterogeneous equilibria is we never, Spanish, never, nunca, never include solids and liquids in an equilibrium expression. So when you go to write an equilibrium expression, if there's solids and liquids in the equation, do not put them into the expression. If you look right here, here's an example of heterogeneous equilibrium. If you zoom in on this, there's a solid, there's another solid, and there's a gas. So the first thing I would do is not put those into the equilibrium expression. So it's just products over reactants. Since I just have a product, it would be the concentration of CO2, stoichiometric coefficient's 1, so the power of 1, and then nothing on the bottom. That's my K expression. Now, here are some K expressions that you should be able to do. Products minus reactants. If you look, this is homogeneous equilibria. So what do? I take the product, which is right here, SO2, Cl2. I put the concentration of SO2, Cl2 as a gas in brackets. The coefficient for it is 1. So I don't really write the 1 there, but technically just by writing one of them, we assume it's 1. On the bottom, what am I going to do? I'm going to take the Cl2. Cl2 goes in brackets. Remember that brackets mean molarity. SO2, put that in brackets, goes on the bottom. And that's going to be equal to Kc, which is the K for concentration. If you look right here, the next one, B. I go to do that one. Start with products. I'm going to write NO, brackets, exponent 2. I'm going to take the, remember, coefficients become exponents, over concentration of oxygen. In that case, the coefficient is 1, and the concentration of N2 is equal to Kc. So that's how you do homogeneous equilibria. Heterogeneous equilibria, we have to look. Remember, that is a solid, so that is not included in the expression. So for A, I would take the products, CO, concentration of CO, to the second, over concentration of CO2 to the first is equal to Kc. Look at the next one. If I look right there, I have a solid and I have a solid. Therefore, those two cannot be in my equilibrium expression. I take that's a product. So what I'm going to do is I'm going to take the product, which is HI, bracket, to the second, over H2S as a gas equals Kc. Notice my coefficient there, 2, becomes my exponent right there. Coefficient there is 1, therefore my exponent there is 1. Next one. One of the things they can have you do is they can ask you for Kp. Kp is an expression of gas pressure. So if they give you all gases, you can do it either for C or B, Kc or Kp, excuse me. If you decide to do it for Kp, the symbols are different. Instead of using brackets, use P to represent pressure, with the subscript to remember whatever or to denote whatever gas it is, and then your coefficients, there are your coefficients from your chemical equation, and that equals Kp. So basically, if you want to use partial pressures, if they gave you atmospheres, it has to be in atmospheres, and they asked you to calculate your Kp, it's the same idea. Products still go on the top, reactants go on the bottom, you still use the coefficients. Now, one key calculation is there's a mathematical relationship between Kp and Kc, and you're expected to be able to calculate them. Here's how it works. It's basically Kp right here is equal to Kc RT to delta N. What delta N is, number of moles of products, gaseous products, minus the moles of gaseous reactants. So it's products of gases minus reactants gases, and that is delta N, is change in the number of moles. That becomes the exponent for R and T. T has to be in Kelvin. And if you look, here's an example. R is the gas constant, 0.0821, that we use in chapter 5. If you look, what is the following equilibrium? For the following equilibrium, what is Kp? So they're asking you to find Kp. They give you Kc. We talked about what the mathematical relationship is. It's a formula. You're going to plug it in. What do you need? First, you need temperature. If it's 700 degrees Celsius, what you do is you take 700 plus 273. You get 973 for the temperature. R is a constant. Plug in R, so we have T, we have R, we need delta N. Delta N is number of gaseous moles minus product moles minus reactant moles. If you look right here, I have a total of 2 moles of products on that side. If I look on this side, I have 2 here and 1 there, 3 moles of gaseous reactants. So then what do I have to do? It's going to be 2 minus 3, which is going to equal -1. So my value for delta N is going to be -1, and all I'm going to do is come back and plug it into the expression. So I take the Kc that they gave me, inserts right there. R is just 0.0821 liters, moles, atmospheres. Temperature is 973 degrees. Last but not least, I add the exponent, which again is number of moles of products that are gases minus moles of reactants. You do your calculations and you convert it to Kp. Here's an example of the type of problem they will have you do. If you look here, they want you to find Kc. So you take the same thing. Kp is equal to Kc times R times T delta N. What do you need to do? Well, first, the temperature is given you in Kelvin, so it's 303. So I put 303, Kelvin goes right there. R is going to be 0.0821. I should write the units, but I'm kind of trying to go through this pretty fast. I'm solving for Kc equals Kp. The Kp value they gave me is 2.9 times 10 to the -2nd right there. Last but not least, I need delta N. To find delta N, I look at moles of gaseous products. I have 1 mole there. 1 mole there, so that's 2. Gaseous reactants, I have 1 mole. So 2 minus 1 is going to be 1. So it's going to be basically my delta N value is going to be 1. So it's basically that times that. And then you just mathematically solve for Kc by taking these, cross multiplying down to the bottom. And this is what you end up with. You have the 0.0821, 303 to the first. 2.9 times 10 to the -2nd. That's your Kp value. So you isolate Kc algebraically. You calculate your value to find Kc. Those are equilibrium calculations that are pretty easy. If you look back at the next one, how many moles of gaseous products do I have here? I have a total of 3. I have 2 there, 1 there. I have 2 on that side, so I'm going to take 3 minus 2 to find my delta N. My delta N value for this one would be equal to 1. Then this last one, if I was doing this one, if you look right here, I have 1 mole on the product side, 2 moles on the reactant side, so my delta N value for that equation right there would be -1. gaseous products minus gaseous reactants gets you your delta N value. Then it's just a matter of plugging the values into the equation. All right, make sure to complete your homework.